Ralph Bundy is a physics teacher and one of our main go-to guys when it comes to anything science. So without further ado, Mr. Bundy.
Okay. Thank you very much. Thanks for joining us in this, I don't know, is it the first collaboration?
Yes.
This first collaboration between the Viz Arts Gallery and the Rockville Science Center. So hopefully there's a future here with a lot of potential. And the only thing lacking, I think, is the will. So maybe there's enough of that around to make it go. I claim short-term memory loss and a lot of long-term memory loss as well. So if you'll indulge me my notes, I'll sort of go back and forth. Mostly this is going to be a history lecture. Hopefully it's accessible, various parts of it, to different ages. We'll see. Okay? Give me a sign if you don't understand what I'm saying. All right? Okay. 4 parts. One is my motivation as a teacher. Second one is a history of light, which I hope to do in about 15 minutes. That's 2,500 plus years in 15 minutes. Something like 92 billion seconds, something like that. Maybe it's quadrillion, I don't know, it's a lot. I actually figured it out. It's a lot of zeros. Okay? Something about your history with light, if you can relate to that. And then just to follow up with what could be future prospects. Okay, so my history. As a veteran physics, chemistry teacher, 45 years at the high school level, I really measure my success, I think, by how much I motivate young adults to, yeah, I'm just going to go ahead and read this because this took me about 2 days to write this one little card, okay? I'll read you this one little card because it's, I'm sorry, it's 2 cards. It's very important to me. The extent to which I've been able to motivate young adults to rationally question what they are being taught. Some call this active learning. I call it, in the words of the poet Rilke, learning to love the questions for themselves. For me, this means encouraging the student to formulate questions that promote reflection while carrying the argument forward, value their own creative imagination, have a tolerance for ambiguity, because I want them to have a tolerance for me and I'm often ambiguous, require consistency in explanations, test for predictability whenever possible, appreciate that data must always fit the model, and never forget the model is not the thing itself. Which, if I may mention, light has had many models, and none of those models are light. For 2,500 years, we've been fascinated by it, we've looked at it, the artist has attempted intuitively to capture it and affect you with it, and we don't know. We have models, and I'll discuss some of those models. Okay? Before I go any further, I would like to, if I'm unemotional enough to do it, share with you Rilke's answer to a young poet who was anxious about being a poet. And he says, "Have patience with everything unsolved in your heart, and try to love the questions for themselves, as if they were locked rooms or books written in a foreign tongue. If the answers are elusive, it's because you are not able to live them. And the point is to live everything. Live the questions now. Perhaps then, someday, far into the future, you may gradually, without even noticing it, live your way into the answer." Okay, 2,500 years ago, Empedocles, taking a religious point of view and his own speculation, determined that when Aphrodite constructed your eyeball out of earth, air, fire, and water, those were the 4 known elements, by the way. We now have over 100, and none of them are earth, air, fire, or water. That she allowed the fire that was in your eye to point and send out the light, and it would bounce off of the object and come back to the eye. That idea held up for 200 years, even though there were people complaining that they couldn't see at night and they wondered what happened to their eyes when dark arrived. But it was, it was adhered to. It may have fit the times, who knows. Year 300, Euclid actually looked at reflection and applied his geometry to it. By the year, I think mostly he dealt with mathematics and his own speculations. He did have the idea that light traveled in a straight line, but it did not come from the eye. He was convinced. Lucretius, who followed him, also doubted that it came from the eye. And it took until Heron and Ptolemy to actually make observations and change people's viewpoint. Now, Ptolemy was an interesting character. Ptolemy believed that the Earth was fixed, the planets revolved around it, the sun revolved around the Earth, but he was a careful measurer. And he realized for maybe the first time that the Earth had a bounded atmosphere. Because when he looked at the stars, he found that the starlight, depending on which angle he looked, was refracted more or less. So he was the first one to introduce refraction. However, believing that the Earth was the center of things fit into the Judeo-Christian religion at that time, and being the center of all God's creation, they liked it a lot, and all questioning stopped for about, I'd say 1,500 years. That's a long time. In the middle of that 1,500 years, there appeared in I don't know, I'm beginning to hate words anymore like the Middle East, the Far East. It doesn't make sense. That part of the world, he was Islamic, and they kept thinking alive over what Charlemagne called a few centuries without a bath, when people weren't asking questions, and it was like, it took a long time, I guess I should say, before folks started questioning again. And when they did start questioning, it sort of just released everything. And we had what was called the Renaissance. So in the Renaissance, people start looking, questioning, experimenting, asking about things. And to get right into the difficulty, on December the 25th, 1643, Galileo died, Newton was born, and in the words of Alexander Pope, and God said, "Let Newton be," and all was light. My own opinion is it wasn't so much light as it was heat, and there were a lot of arguments, and they had the light as a wave proponent, they had the light as a particle proponent, and the battle was joined. Newton was convinced that light was a particle. Newton did a lot of other really neat things. Newton's enemy in England was a man named Robert Hooke. Robert Hooke, when Newton wrote his first paper on light and colors, Hooke said, "Everything in his paper that is original is wrong, and everything in his paper that is true, he stole from me." He also blackballed Newton from the Royal Society at one point, at the first point, but Newton got in later. In the meantime, there was another guy in Holland called Huygens, and Huygens actually worked out the mathematics of wave behavior and worked out the mathematics for wave behavior of light. Now, because England wanted to be the best, and because England really wanted to have the whole world know that their scientists were better than the other guy's scientists, put up a big campaign to make Newton top scientist. Not that he wasn't a really good scientist, but he then became so respected that folks held on to light as a particle for a couple of centuries. Newton shot himself in the foot. Newton proposed that if light is a particle, when it goes into glass or water, it has to speed up because he had his laws of mechanics, and he was applying laws of mechanics to light and optics. The first really, really big mistake, okay? Because later on, when Fizeau actually measured the difference between light and air and light and water, and showed that light travels slower in water than it does in air, Newton was in trouble. So this brings us to just about 1800s, 19th century. In the 1800s, a man by the name of Michael Faraday, who is a semi-hero of mine because Michael Faraday had very little mathematics, but he had a really creative, intuitive imagination. And he figured that all of space must be filled with lines of force, with fields, along which light could travel. That it was the nature of space. Prior to that time, let me take an aside here and just think about it. Imagine a flag that is waving. Take away the flag. Where's the wave? Imagine water that is waving. Take away the water. Where's the wave? So they were convinced something had to be waving. The first name they gave to it was the plenum. The second name they gave to it was the, if you'll excuse me, I have to speak one of my native tongues, Scottish. It's not a native tongue. I was part Scotch. It's the aether, the all-pervading aether, that when you smack the aether would respond in such a way that it would carry the light from one place to another. It presented a problem. Descartes, for instance, who was a Flinham person, actually said that he based his whole philosophy on the speed of light being infinite. It's like a pressure wave in Jell-O. If you hit Jell-O on one side, you get a big block of Jell-O, and you hit it on one side, the other side will wiggle. And he thought that happened instantaneously. Well, he was discredited on that several times later. So the big problem was, if there's a wave, there has to be something to carry the wave. And so all of space was filled with this aether. And Faraday avoided the subject by using his lines of force and said he wanted to dispense with the aether and introduce his lines of force. James Clerk Maxwell, who was the premier mathematician, took Faraday's ideas, put them in mathematical form, and according to the physics of the time, put the capstone on physics. Everyone thought light was a wave. They were convinced. Maxwell had summed all of physics into his 4 equations. And in around 1880 or so, people in physics were saying things like, physics is over. We only have to calculate the decimals with greater accuracy. There's nothing more to be done. The edifice was complete. Shortly thereafter, there was the discovery of the electron, and the edifice began to crumble. Okay? Now here you are, what, 100 years later? And think about what has happened in that 100 years. Okay? Those of us who are a little older have seen some of this fast, accelerated pace of technology. Some of us who are older are almost breathless considering this. My 2.5-year-old granddaughter is very adept at pushing buttons. If they don't hide the remote, she turns on the TV. And she selects her DVD, Dora the Explorer, and you know, you'd have to watch her all the time. So I got a message from Dora the Explorer. You know, everything can be a learning experience. Dora the Explorer teaches me that we're all explorers, right? And whether we explore with art, or whether we explore with science, or whether we explore with swinging on the bars at the playground, we're all explorers. So that's a little bit, I think, what drives humankind and what makes humankind what it is. That in one way or another, we're all explorers. So, what happened over that time? Light was a particle. Light was a wave. No, it was a wave that, you know, bunched up like a particle. No, it was a wave of particles. No, it was a particle that waved. It was a mess, right? They couldn't pin it down. Anyone here not believe in atoms? Everyone here's heard about atoms? Not believe in atoms? Okay, you better believe in atoms because you're going to be tested on it someday in school, and you have to make an A, so you have to believe in atoms, right? So, if I can make an analogy at this point, I I'd like to propose that light, now this is really going out on a limb, light is not a thing. Light is a process, just like sound is a process. And just to talk about you folks, when the cap came off of the big, bottle of champagne in the sky, in space, when the cap came off and every bubble was a big bang. You see, the Big Bang did not happen with just one little big explosion, as I first thought when I was introduced to the idea. It happened everywhere, like opening a bottle of pop and the bubbles come out. Take the pressure off whatever it is we're embedded in, take the pressure off, and the bubbles come out. And the bubbles come out with great energy. And as time passes and that energy, that heat cools, you get different kinds of particles that are of lower energy. And finally you get to this one little planet going around a, moderately sized star at just the right distance away from the star, that the energy is right for life to form. Now, does this mean that the universe from the beginning is set up to produce life? It happened. Here we are. Okay? Now, I believe in evolution. If you don't, shut your ears, don't listen. I believe in evolution. And the first thing that we could see was shape and outline. And it's still with us in the large ganglia in the eye, so that we can become startled by a shape or an outline. It's fight or flight. And it's there. Color only came later. And they determined it comes in 3 little colors. Not the cyan, magenta, and yellow, although you don't see the magenta at this point. Not the cyan, magenta, and yellow that you see here, but red, blue, and green. And that's the way you see color. But an interesting thing that artists have discovered is that you really don't see pure color. You see color only by comparison. That your eyeballs are fixed in such a way that you only get the color by comparison, so that if you took 2 identical red squares and you embedded one red square in dark blue, you would see a dark red. If you embedded that little square of red in yellow, you would see an orange square. So your eyes are doing some funny things there. And what's it all about? At first, it was nothing but survival. Maybe you didn't need to identify color. Later on, the color develops, and along with color developing, consciousness develops. And as consciousness develops, perhaps reflection, perhaps spirituality, and what happens? You start to create. You start to build stuff. You start to add to your environment. And so you come to a point where, I hate to show this. how many of you, how many of you look at this as an antique? It's 3 years old. It does nothing much, but you know, I can call on it. The light goes out, and I hit it, and the light comes back on again. That's a picture of my granddaughter, by the way. Do you ever ponder where the light comes from? Does it ever amaze you when you're at your computer and you hit the E key, that an E appears on the screen? No, you don't think about those things. You know, it's surface, it's superficial. So we're in a tight spot these days. We're in maybe the same kind of shape that we were in the Middle Ages, when people were just being, right? So when the Renaissance came, people were becoming. In the Middle Ages, if your father plowed the field, you went out and you plowed the field. That's what you did. That's what other people did. You went to the church. You looked at the symbols. You can get some idea of that from the art that you see. And then when you get to the Renaissance, what happens to the art? In the pictures, the windows open up. Nature comes in. Color is explored with. And the artist is learning some things that you may not be familiar with. And they're not even familiar with, but they know it in their bones, in their eyes, in their brains, right? So, you are capable of only 100-fold identification of light and dark. Think about that. In other words, it's like my daughter, who's a musician. Can you hear half notes?
No, you can't hear well, I mean, you can count how long a note lasts.
Right.
But you don't hear a half note, you hear a tone. You hear a
So
wave.
what's the vibration between what you can hear and the next nudge up?
Oh, you mean like a half step?
Oh, a half step. Okay. See, I don't know music.
Is in Western music. Now, if you go to like Indian music, they have quarter tones. So it's you know, so it's what our ears are attuned to. It's what our musical system is based on, and the Western musical system is based on.
Yes, sir.
The human ear and mind are capable of distinguishing between very tight tolerance of frequencies, like down to a hertz or two range. So it's actually, you can distinguish between, 400 hertz and...
Spoken like a true scientist. Yes, sir. Thank you very much.
403 hertz. Between those two. Yeah.
400, between 402 and 403? That's
down to
really
hertz.
great acuity, I think.
There's a lot of discrimination for hearing, yes.
That's really neat. Now, can you do the same thing with light and dark? I don't think as much.
65,000 colors?
Right. There's these shades of gray, right? Now, nature in the sunshine is about 100,000. So when you go from dark to light, your iris are going to just panic, right? They're going to squeeze it right in. And very often you'll also squint. And you really need time to adjust. Now, what does the artist do? Within a single painting, they're going to affect you more if they can produce in that painting no more and no less than about 100 different gradations of light and dark. So the light and dark in the painting is just as important as the color. And then when the color is superimposed on the light and dark, it's the illuminance that makes it either stand out or blur. And they've played with this for years and years and years. So I would encourage you to study art with a different eye and develop an artist's eye and study your environment with a different point of view. And what can I say? I wouldn't want to call your brain scientific. I'll just say, and let your rationality pervade over your initial reaction and begin to think about stuff. So I think that should do it. Although, what about the future? Maybe some of you can tell me about the future. Where are you going to go with this? Where is this technology going to take us? Is it going to swamp us? What have we done, you know? It can't swamp us. No. We've got, you know, we're the human race. We got to do this. Look what we have. The laser. Light amplification by, you know, bapping an electron just in resonance with what it's already capable of doing, and you amplify it. You amplify the light that comes off of it, and all of the things that you drive with it. You drive what? Door openers, you drive music players, you drive all sorts of things with lasers that are just buried in there that you don't even think about. High intensity LEDs, just in time for us to run out of energy, just in time for us to, you know, realize we have limited resources. There's no hope. But there is duct tape. So, so we can put duct tape on it. So, you know, I think there is the opportunity, and maybe, again, the only thing that's lacking is the will, the creativity, and excuse me, young students, reading books, and some of the more professional folks applying seat of pants to seat of chair for extended periods of focus time, things like that. So I do think that it's an exciting time, especially with light. We become enormous consumers. We're voracious. We're using it up as fast as we can use it because we like to sell stuff and make money and give you a new gadget and stuff like that. Thank you, Steve Jobs. So thank you very much. And help us out, folks, all you young guys. Just remember, we're counting on you. We're over the hill. Thank you. Yes?
I actually have a question.
Oh, okay.
What's the current thought on where the light as wave or particle, you know, where does the current thought on that stand? Or are we still just as confused as we were 50 years ago?
George Gamow wrote a book called 30 Years That Shook Physics. From 1900 to 1930, physics was in a definite quandary. The point being that quantum mechanics has to resort, because they owe allegiance to their physics. They have to resort to classical mechanics and verify their quantum mechanics with classical mechanics. It's an anchor around them that I think drags them down. Okay? Think about it. An electron, this is an atom. this is a let's say an electron that if I bang it, right, or if I get it into resonance, and the vibrations become so much, touch it. There's energy there. And an electron in an atom somewhere changes position, the electron accelerates, a photon comes off. At what speed does the photon come off?
I'm sorry, doesn't the electron fall back into a lower orbit?
Yes.
For the electron
Right.
to come off? Okay.
The electron falls to a lower orbit, a photon is emitted. At what speed is the photon emitted?
Speed of light.
Speed of light. Classical mechanics says you've got to have an accelerating period. You cannot go from 0 to the speed of light. Think of that. Nothing to the speed of light in no time. Therefore, can't do that with mass. Therefore, photons have no mass.
As far as the photon is concerned, did it ever exist?
Pardon?
As far as a photon is concerned, does it ever exist? It's traveling at the speed of light. Time does not pass at the speed of light. So does it ever exist as far as it's concerned?
I love you. In my most private moments, never to tell anyone, I will think, maybe there's no such thing as light. Maybe it's all just space. Maybe it's not the speed of light, but the reactivity rate of space, right? Now, what can space do that you can't see? What about space? Nothing, right? No. Space is not nothing. Space is no thing. And what can space do? Space can evoke the woof and the warp of magnetic and electric fields. And when that electron accelerates, you get a magnetic field. And that magnetic field stimulates an electric field, which stimulates a magnetic field, which stimulates an electric field, at exactly right angles to each other. That's equivalent to me taking this bowl and pushing as hard as I can, and the bowl goes flying out that way. It does not make sense. Okay? Now, where does that... I am really digging a hole here, okay? Where does that electric and magnetic field come from? It's point-oriented. It doesn't move. It only appears to move because it's a eliciting effect from, one to the other. Where does it come from? Your guess is as good as mine. But then, we talk about other dimensions. What's in other dimensions? Is it coming from another dimension? Is it... I'm rambling on. I hope you don't mind. I love it. And if bear me out. Suppose that your universe was like this, two-dimensional, right? You had no knowledge that you were embedded in three. This comes from a man by the name of Abbott, who in 1900 wrote Flatland, and engineers have picked up on it since and written other sequels to Flatland. Suppose you're on this little thing and that's all you know. You only have two ways of moving. And somebody goes, and you go, oh my God, I'm surrounded, right? You didn't see it coming. Or suppose that a ball goes through your space, a three-dimensional ball goes through your space. And the three-dimensional ball begins to you. How? As a dot, and then as a little circle, and then it grows, and then it shrinks to a dot, and it's gone. That's all you know. And you go, oh my God, I've seen a ghost, right? It is something that is able to intersect with your dimension. Projective geometry for the mathematician, right? Now, what if you're able to take your imagination, if you can do it from 2 dimensions to 3, and imagine from 3 dimensions to 4? Where is the 4th dimension in your surrounding? Go back to the sheet of paper. Where is the 3rd dimension to its surrounding? If only you could get to it. How far would you have to go to get to the 3rd dimension? But you can't get there, right? It's forbidden to you. Now, go back to the 3rd dimension. Where is the 4th? Right here on the tip of my nose. Right here at the tips of my fingers. It's everywhere. We're embedded in it. So, I propose for the first time in public ever that electric and magnetic fields are the basic constituent of the 4th spatial dimension. Don't quote me. Now, back to this particle wave quandary. 1930, they're having conferences all over everywhere. They're arguing like crazy. Niels Bohr is saying, if I had known when I was in school that physics was going to be like this, I'd wished I'd become a circus clown. Right? One of the schools of thought, the Copenhagen school, says, okay, we cannot figure it out. It's both. It's both a particle and a wave. If you look at it when it travels, you'll get a wave characteristic. If you look at it when it interacts, you'll get a particle characteristic. That's it. And following up on that, a man by the name of Richard Feynman developed a very clever, extremely clever model to predict. The model has worked in every case. No matter how the technology produces the ability to get to the next decimal point, it's still correct. It has never been violated. And it goes like this. You got a little clock. See? Looks like a particle, doesn't it? We don't care. It's a little clock. It's emitted from a point. As soon as it's emitted, if it's a red clock, the hand moves kind of slowly. If it's a blue clock, the hand moves faster. There's more energy in the blue clock than there is in the red clock. When these clocks emitted by the billions and zillions and I can't get to that high a number, are emitted, they go, because light can travel in any direction, it goes in any direction. It goes in all directions. And it comes back in from all directions. So chances are, statistics intervenes, chances are that a red clock is going to hit a point when another red clock hits that same point. And you're going to see red. Your sensory mechanism is going to respond to red. And that's it. That's where we are.
So it's a wave inside a particle.
No, it's a little clock. It's a little clock with a hand, right? And it back to the model is not the thing. The wave is a model, it's not light. The particle is a model, it's not light. Feynman's little clock is a particle, is a little clock, it's not light. Mathematicians, let's one last thing with mathematicians. Take a spring, put a mass on it, bounces up and down, okay? Take that through space, you get a sine wave. Or it could be cosine wave, depends on where you start. Sine or cosine, that's all, that's it. Simple harmonic motion. Take a circle, well, no, take a stick. Take a stick and have the stick rotate in a circle. That's all. As the stick rotates in a circle, make the stick move, right? As the stick moves, plot how it looks this way, just like a spring, right? And what do you get? You get a wave. Maybe there's no wave, you know? So if something rotates, right? That's all it takes. Because if our universe does not exist, mathematicians will create it for us, right? And I'm not the first to say that. I just loved it when I heard it. Because why? The ultimate model is the mathematical model. It's the fire that our feet as scientists is held to. So I hope that's it. Thank you.